So question 3, at the swimming pool, Jess and Rima are at the local pool. They notice that there is a shallow region at the edge of the pool. Waves travel through the deep water and change direction as they slow down, moving into the shallow water. So we can see the shallow water there on the bottom. On the diagram below, draw waves that have entered the shallow water. Also draw an arrow showing the new wave direction. My preference for these questions is to draw the arrow showing the direction first, because that gives you a reference point to draw your new waves. So because we're going from deep to shallow water, it's similar as if you would be moving from air into glass or something with a higher optical density. So we're going to bend towards the normal. Okay, towards the normal. So from this point we can draw wave fronts in excuse me, perpendicular to this, because wavefronts are always perpendicular to that direction, trying to draw a perpendicular thing on these ones. So that's in the deep water. In the shallow water we're going to go across, and we'd probably have some more coming across here, carrying on the old ones that are there as well. You can make them longer if you feel the need to. And my terrible drawing using the stylus that is like a fingertip is very difficult. I'm investigating in something different, but anyway, that's what you'll get. The waves are definitely closer together, so the wavelength has decreased. Actually, we're getting onto the second part, so let's just go straight into that. State what happens to the frequency and the wavelength of the waves when they enter the shallow water. Well, the frequency stays the same, or no change, and the wavelength decreases. So we can see that the wavelength gets shorter. Yeah. Frequency always stays the same with these sorts of questions. Moving on, there are two pipes dripping water into a shallow pool. This is also a classic question, making circular waves. Rima notices that the dripping water produces an interference pattern in the pool as shown in the picture below. So let's just investigate this a little bit. We've got over here the two pipes that are dripping, and we've got the troughs shown here and the crests shown here. So the crests are the white parts that's sort of going around there. I'm experimenting with a new arrow in case you haven't noticed. And the troughs would be the darker parts in the centre. Okay, so excuse me. Moving on to the question. Oh, I guess we've got to identify these antinodal lines as well. Antinodal line, the central one, and we would have nodal lines also kind of in the centre as well. I think they might be going to ask about that, or maybe draw where you would expect an antinodal line to be. Anticipation is a really good skill, but let's move on. C, explain what would happen to the position of the first antinodal line with respect to the central antinodal line if the frequency of the drips increased and if they remain in phase. So let's see, they're remaining in phase, so that's not going to be a problem. That's just maintaining the conditions for interference. So frequency has increased. So this is an example where the frequency changes. It's not the same wave that you had initially. You're creating a completely new wave, so that's why the frequency can change. The wavelength, we're not sure quite how that's going to respond, but the wave speed has to be the same, no change. Okay, so from our V equals F lambda, you can see that if the frequency increases, the wavelength is going to decrease. Okay, so wavelength is going to decrease. The path difference to the first antinode, where are we? Going down here. This is what it says in the marking schedule, and you can deconstruct it a little bit, but the path difference to the first antinode is one wavelength. Okay, I would probably interpret that a little bit differently, but what you're essentially saying is that depending on the wavelength depends on the spacing at each of these different positions along there. If you have a smaller wavelength, maybe we should draw it. Let's draw it. I'm going to bring you right across to the side. I'm going to compare. So here's a large wavelength, and here's another large wavelength. And we're going to keep those. That's by itself, you can't really tell much. But here's a ginormously large wavelength, and we need to have just enough to show what's going to happen here. So these are the points where they're kind of crossing over in the middle, and there's our secondary one just off to the side here, and you would have another one out here. So let's draw those two lines on. Now what I'm going to do, using the magic of explain everything on an iPad, I'm going to make the wavelength half as short by going over the top of it like so, and we're going to see what's going to happen. Okay, so yeah, you can see what I'm doing, eh? It's a little bit messy, but we'll do our best. From the other side, there, halfway between, well, that one was on it, this one's halfway between, and there's halfway between. Maybe I should have used thicker lines, but the central line's obviously going to stay where it is. But you can see that we've got new points where those peaks are crossing over that have drawn it closer together. So this is what they're trying to indicate, I think, when they say that the path difference to the first antinode is a wavelength. But if we've made the wavelength half, as we've done here, we've effectively halved that distance that we initially had to the first antinode. But you can't really talk in terms of wavelength to the first antinode if you're talking about it striking a screen, as a lot of the time we are, because it's spreading out basically, so the further back you put the screen, the further away the distance is. So you need a very clear reference point. So anyway, I think that's answered it. I think we'll move on. Just double check the frequency. What would happen to the position of the first antinodal line? So it will get closer, definitely get closer, because the wavelength has decreased. Yeah. And you can demonstrate with the diagram conclusively. Next part D, the diagrams show waves approaching two different sized gaps in a harbour wall. There's always a harbour wall and always boats. That's alright though. It's tempting to just draw straight on that, but let's read the question. Name the process by which the waves could reach positions A and B. The process is diffraction. Just something to memorise. Waves bend through gaps. That's diffraction. And around corners. Part 2, explain whether the owner of a boat, this is an explain question, so you're not just giving a simple answer, whether the owner of the boat would do better to anchor his boat at A or at B. Support your answer by completing the wave patterns in the diagrams. Okay, let's see, just adjusting my position. In the first diagram on the left hand side, we've got the wavelength is very close to the sides, so we're going to get the maximum diffraction, and I haven't drawn this particularly well, but you get the picture. So you get max diffraction, which means you're more likely to have an up and down kind of thing going on at A. With B, there's going to be less diffraction. The majority of the wave will just carry on straight through, and then you'll have more. Oops, I've really got to work on getting my wavelengths right, and you'll have a bit of bending around the edges. So B is less likely, so you will just say less diffraction. There we go. So using that bit of information, we would suggest that it is better to be at position B because there is less diffraction. The solutions I'm just looking at now also give that. They want to see that the wavelength remains unchanged, so my terrible drawings initially weren't very good. In fact, if I was being really pedantic, I would suggest that this is not a good wave because there's too much space. If you're not very good at drawing these sorts of things, you might like to state really categorically that the wavelength should be unchanged. They're not trying to assess your artistic ability, so if you can identify by making a bullet point and just writing it, then they'll be happy with it, I think. Okay, and the solutions give exactly the same thing. Yep, lovely, there's nothing more to add. Is there another question? No, that's it.